Swayam Prabha. Digital India. Educated India.
Y'all have any? Good morning, everybody. We'll start with that. Okay, I think we'll get started. It's 9:35. So yesterday, sort of this is bonus material, so to speak. So yesterday had a question from Amit regarding the decay functions and how they look like. I showed you, I think we've uploaded those curves, right? Yesterday, we've uploaded some curves that Kaviyarasu had plotted, and we've also uploaded some equations. But I just wanted to give you some idea of how some of the decay functions look like. So we'll start with that. So basically a question that was asked. So if you look at the Friedlander equation, it's given as P of T is the positive pressure and 1 minus T over the positive duration e power minus Bt divided by Td plus. And so for an expression like this, your Z, this is for Z is in meters, this is in units, SI system units, and the range of applicability from 0.1 to 10. And for something like this, B, the decay function, is given as, and this is where I was talking about, you might question why it goes into so much of decimals. So this is 5.27 Z power minus 1.1975. So this is one example of a decay function. Another example of a decay function, this is where you'll see uncertainties. We look at a curve and then we think about, I mean, even I started thinking about the same way. There is a nice curve and everything. Once you see something printed in black and white, you think, we assume automatically it is the ground truth, right? But not quite, especially in these areas. Most research or applications, it's not quite the case. So let me give an example. Let's say you have the standoff distance is 13 meters, and you'll see a different expression. So W is 750 kilograms. So from this you can derive these two data, you can derive Z is equal to 1.43 meters per kg power 13. And you see that this is greater than 0. And for these parameters, you get PSO is equal to 415.5 kilopascals. Then IS, this impulse is 1144 kilopascal millisecond, and T naught positive load duration is 15.3 milliseconds. So there is another decay function, and this decay function expressed in terms of Z. So it's given as B is equal to 0.2 plus 13.77 0.55 divided by 1 plus exponential or E power Z minus 1.13 by 0.18 plus 1 minus 0.55 divided by 1 plus e power z minus 1.04 divided by 1.83. And this is valid for 1 less than z less than 10. So, as you can see, the decay function is clearly not a constant, and it is a highly complex function. So, if you calculate in this case, so for z equal to 1.43, b comes to 4.48, and the Freelander function is, so if you're developing some analytical work, you can definitely use equations like this. I have a couple of references, not sure why it's going there. So this is 1 minus t divided by t naught e power minus 4.48 t divided by 15.3. Alternatively, when you expand the exponential functions, let me take another example. In this case, for z less than 1.0, so that was for z between 1 and 10. So let's say you have, I've done this calc. So assume, so this is a high case. So and p naught is, and z comes in this case, I'm not given the r value, z is 0.71, and so here you will see that this z is less than 1.0. And P naught is 1925 kilopascals, with IS is 30 to 35 kilopascals millisecond, and T naught is 16.4 milliseconds. So if you compare here 1925, 415, so there is sort of an order of difference, not quite, but 5 times at least. And the impulse is also higher, 3, but the T naught is about the same. But z in this case is less than 1. So for here, a suggested equation for B is 22.35. And I've seen these expressions in a publication. I'm not sure they did any sensitivity analysis to see if you can remove the decimals. I would recommend you try that out. It's better to have some clean numbers. I don't think if the decimals are going to be so influential. But you see, this is 11. I'll just put the without the decimals, z cubed. Maybe because z is less than 1, they are going beyond. So 22101.2 z power 4. It keeps going. You have to be patient. No, I'm just joking. 23788.69 z power 6. Then it is plus, there is another one, plus 3283.57 z power 7. No, I'm sorry. This is 23899 z power 5, and there is minus 13737.9 z power 6. So that is 1, 2, 3, 4, 5, 6. And so for z equal to 0.71, your B comes to 8.5. But the numbers, if you look at it, the decay coefficient is 4.48, and you can plot and for yourself and try it out. So your expression for the Friedlander equation is 1924.8 1 minus t divided by 16.4 minus 8.5 t by. Maybe this afternoon, I think we can make a note of it, Kabir, or that we can add this. Maybe they can plot it and just get an idea of, for different z values, how these equations look like. And Excel, yes, we can do it in Excel. So we haven't scheduled it, but I think it's a good idea to try it out. So this hopefully addresses the question that was asked. If you want references, let me know, and I can give you more of where this comes from. Oh, let me make sure I'm not overwriting it. Okay. So we'll continue yesterday's example of a petrochemical. It's very I think yesterday we had completed a front wall. So let's complete the example for the front wall loading. Two more things we'll look at is the side wall, and if you have not completed this exercise, you can finish that also today and make that comparison. So we'll have that first, then you can do the Friedlander or whatever order you want to do, and then we'll add today's exercise. So CD, for a side wall, CD, as you know, is minus 0.4, and then you had the length of the wall divided by L1. Side wall we are considering, we had a lot of discussion on what L1 should be, 1 feet. So LW is the blast wavelength was 237 feet, and we are considering 1 foot here. So this is 237, and if you see the figure, I don't know if you have that, but it's there from UFC. It goes like this, more or less, and this is at about 10. So anything beyond that, so from here you get CE equal to 1.0, and PS is CE PSO plus CD Q naught. So this is 1 multiplied by 9 plus minus 0.4 multiplied by 1.8 is 8.28 psi. Then we have the rise time, which is L1 over U. This is 1 feet, and U was 877 point something. So let's say 870 feet per second. So this is 0.011 seconds, approximately 0. and TD was given to be 26.6 seconds, milliseconds. So notice one thing, there is no negative curve in these. The effect of negative curves are, especially low pressures, are fairly minimal. So I don't remember what the arrival time was, but no, actually you can take this as the arrival time, but the loading itself, if you're plotting for design purposes, this portion is what is important. And so this is 1.11 plus TA, and this is 26.6 plus TA milliseconds, and the peak value is 8.28 psi. The rear wall also is pretty much the same. But slight differences, the overall pressure still remains the same, the back wall or the rear wall. So drag coefficient again is minus 0.4. The equivalent load coefficient, so the load coefficient is given as LW divided by S. And LW was this is the wavelength, 237 feet. And S is the height, the lesser of the two. So in this case, this was 11 feet. The height was 11 feet. And so this comes to 21.45. So again, from this, much greater than 10. So CE equal to 1.2. So PS still remains the same. CE PSO plus, I think somebody was asking me what are all the equations. I have it somewhere yesterday, but you can now see it from this example. PSI plus minus 0.4 times. I think yesterday there were questions whether it's 1.6 or 1.8. They should be the same numbers. I think several people asked me that question. So 8.28 psi. Only difference between the back wall and the front wall is arrival time is TA plus TA1, which is TA plus L over U. Now, the building was 30 feet. So here that number 30 feet, and the speed was 878 feet per second. So this is 0.34 milliseconds. Then the rise time is S over U, which is the same, 11 divided by U is 878. So this comes to 0.012 seconds. So this is TR. So T, if you plot this now, bless you. Again, it's going to be very similar. So that value is TA plus 0.034 or 34 milliseconds, let's say. For design, the later part matters, 8.28. And 72.6, and this is 34 plus, let's say, 12 is 46. And all of this, note no negative pressures. So you can compare it this afternoon with what you did yesterday and see how different they are. Yeah. Yeah, in this case, I do not know. Let me see what the yeah 960 feet, but the Z is pretty high, 10. So that means it's quite far away. So by the time it comes to the building, right, its speed has decreased. Yes. Yeah, good observation. Yeah. Mm-hmm. Yeah, it will decrease with the distance. Yes. So we are calculating the shock wave at that distance. Oh, you're talking another 30 feet. Yeah. You could, yeah, you could recalculate the U. Yeah, it's a very subtle point, but correct. You could recalculate U there. Does everybody follow his question? Because the wall is now 30 feet behind, furthermore, the shock wave speed will go down, which is true. And you can even change I calculated it at the front. So I think 30 feet, it was only 12 feet. This was the greater of, sorry, I just looked at the picture. This was 12 and this was 30. So this is the greater of let me go back and check, but that should be 30 there. I'll confirm that. But yeah, other than that, you're right. You can recalculate those values, especially if it is very long. So those are some leftovers. So now we come, just by show of hands, I'm going to cover what I've prepared anyway, but just to get an idea, show of hands, how many of you have had a background in structural dynamics? 1, 2, 3, of course you, 4, 5. So you've had it as a course. Okay, so the others have not had a course in no vibrations. You've had vibration, mechanical engineering vibrations. You would have had 6. You're not. Yeah, that's fine. But you've had a background in it. Okay, and some of it also is some physics part of it. So what we are going to do today is, in a way, I'm glad to know that many of you or most of you have had it, or it's been way back. So I feel good about covering. These are very basic structural dynamics, but what I have taken is principles as applied to blast loading. So you can do structural dynamics as a mathematical course, get intense into integrations, types and all that. And if you actually do a course in structural dynamics, you hardly do anything or very little in applications, right? You might just give one example and do an application and not really focus on the impact of structural dynamics in that application. So this structural dynamics, that's why I call it fundamentals, to understand or as applied the blast response, or rather I should say response to blast loading. It's very interesting to understand where it comes. When I could present some graphs and ask you to run away, look at this graph, get this value, that value, you're done. But here now you'll see why some of those exist. It doesn't just takes a class to review and go through it. So we have discussed this. We'll discuss various concepts. The first concept, of course, is the concept of degree of freedom, which we have talked about. So in general, if I look at a beam, we've seen in finite elements, as we've mentioned, you have degrees of freedom associated with ux, uy and uz, and also you have theta z, then theta x, and this is theta y. So general is 6 degrees of freedom per node, and it depends on where you look at it from a structural perspective. What we are interested, if you do the same thing, some of these are constrained, of course. Let's say you have these degrees of freedom here and here, and you have this degree of freedom is constrained, but these are nodal degrees of freedom. So these are called nodal DOFs. When you are using finite element programs like LSDyna or Abacus or anything else, what you are going to get response back are these nodal degrees of freedom, rotations and things like that. But in the concept of a structural single degree of freedom, we use a structural deflection as a degree of freedom, or a rotation. So in this case, you have a cantilever, and we'll see different types of loading. So although you're still considering a nodal degree of freedom here, you're still considering this could be thought of as uy. Say this is also delta. So this is a nodal DOF, but also it corresponds to a structural DOF. And what we are looking for is a structural DOF, where a maximum response is desired or expected. So we predetermine where that maximum response is and then keep that as a focus to use analytical expressions for deflections. Now, so we'll spend a little time again on absorbing the SDOF equivalence, single degree of freedom equivalence. So starting with, I'll take a few examples and later we'll give you others. So if I have a structure that is subjected to a wind load, and say it is a cantilever, and it's going to deflect in this manner, this is delta, and if this is L, we assume initially elastic behavior. What happens? We know that anything related to blast is likely not to be in the elastic range. So we'll see how to address that using some graphs. So we know in this case delta is equal to PL cubed by 3EI. And so if I take this to be an equivalent spring and a load being applied, I haven't come to the mass part, we'll talk about that perhaps tomorrow. So expressing this P equal to 3EI by L cubed delta is K delta, assuming this. So I get my spring stiffness to be equal to 3EI by L cubed. So this is a structure stiffness. We'll do one more example and we'll see the significance of what a structural stiffness is. Take another simple case. If you have, and you can extrapolate it to multiple types of scenarios. And if you want complex cases, you model it if you can in any structural analysis program, get the deflection from the loads, equivalent load. You have to, we'll talk about that also. So here you have the deflection, and this is delta. And delta in this case is, as we have seen yesterday, 5, this is W by 384, W L power 4 by EI. So from here you can say the stiffness doing a similar expression is 384 EI by, now you express this, anything you have, you need to convert it to an equivalent load. You don't need to have load equivalence. This is equivalent concentrated load. That's the first thing you need to do. So L cubed by 384 EI. So this is P. So this is 384 EI by 5 L cubed. And you can go so on and so forth. So what do we understand from here? The structure stiffness depends on, and you can name some. There's a list, laundry list of different things a structural stiffness is dependent on. 1, the boundary conditions. So you can see, if I take the same thing and apply let's say, yeah, I don't have an analytical expression if I fix it, but if I change the fixities in this case to something like this and apply the same load, the deflection equation is going to be the expression for location, that's not going to be 5 by 384. So it is irrespective of the loading, boundary conditions play a role. What are the other factors? There are 4 factors that play a role. Load distribution, so type of load and its distribution. What are the other 2? Moment of inertia and the shape, so geometry, so moment of inertia and what else? Length, span. So geometry plays a part, and finally the material properties. So 4 different things affect a structural stiffness. That's why we lump everything into one quantity so that it's much. And these are concepts we carry on to when you're especially working on research, these ideas help us to club things together or even separate things out. Quite often you'll be surprised, you talk about, people know P delta curves and they'll say, okay, K value, and they'll do statistics on K values and submit, but really not see when you start differentiating, okay, what is affecting, whether is it the material changes, how geometry changes. So you've got 4 different things to work with. So it's really helpful to think of it from a slightly different perspective. So, and somebody mentioned the type of load and load distribution. So regard to that, if you have anything that is whatever type of loading you have, you need to bring it down to an equivalent load. Now you might ask me, should I bring it down to a distributed load or a point load? It's better to get into a point load. You can try what the stiffnesses are coming from both cases, and that's a good exercise for you to try. Put an equivalent and then convert it to a point load and see if the K values are different. But since we have a spring stiffness model, you get a equivalent load that creates the same moments and shears. Based on, let's say, this is A, sum of moment basic statics is equal to the sum of moments about A, right? Now that we've got that part of the way, because we have defined a DOF, we have defined P. Our spring model is defining K, defining delta, that's of course the metric, defining P. So we've got a model set up. Then let's look at some fundamental structural dynamics. We use a spring damper system. I'll start with a damper also, although I mentioned that damping is not very effective in BLAST, but if you're developing a MATLAB code or any similar code, you have to include the damping and then set damping to a very small value. The program we will use also has damping built into it. Quasi-static loading, damping does play a role, and our analysis includes the range of quasi-static as well. So that's why we will incorporate that. So in a spring damping system, you have a spring and you have a damper represented this way. It's a classic, and this is the load function. So now we are adding an additional damper. So this, we have seen the force is Kx. Now that's your stiffness. In a similar way, a damper, the units in this case, K, we have seen F is equal to Kx. So this is pounds per inch. Now C, this is a function of velocity. So the dashpot we represent by C, and this is a function of speed. So pounds or kips, kilopounds divided by inches per second, or let's say pound seconds per inch. So a damper is force is velocity dependent. And so this whole thing is now represented by a mass and then you have P of t, you have the force is dependent only on x, the displacement, and the dash pot is dependent on c and x dot. And in a dynamic equilibrium, so this whole thing is in a dynamic equilibrium. There are several ways to look at it. I like to put this in the form of a, so this is your free body diagram, then you have a dynamic free body diagram. This is mx double dot. So the force mx results in an acceleration. Mass times acceleration is the force, and this is what you hear often as the inertial force. Accounting for inertial forces in several applications is quite important, especially this one, because this is something that you really do not see directly. So it's easy to ignore. So if I write my basic equation, it is minus kx minus cx dot plus p of t is equal to, if I considering that to be the positive direction, it is mx double dot, or I get the classic expression for the differential equation mx double dot plus cx dot plus kx equal to the forcing. So once again, this is the inertial force. When you look at especially seismic, when you are calculating, this is the damping force that it outputs, and this is the static force or the force due to loads, and this is your forcing function. We will focus on forcing functions as related to blast applications. So what we get quite often in most of our applications, we do high level differential equations, but when we apply it, quite often this is more than sufficient. Starting to build nonlinear differential equations as an application itself is challenging, getting what the differential equation should look like. So this is basically, this differential equation is it is represented as an differential equation represents force equilibrium. Instead of algebraic equations, you have a differential equation representing force equilibrium. And if you look at it, this is basically a second order linear, of course, I have here, this is non-homogeneous differential equation. And if I say P of t equal to 0, it becomes a homogeneous differential equation. So now I can rewrite it That's why I was asking you of how much background or how long have you had. So I can write this as, I can take, let me keep that equation up here. So if I take m out, I get x double dot plus c by m x dot plus k by m x equal to p of t. Now here, let's redefine a couple of things. This term c by m, let's say 2 xi is nothing but C by, let me start with this one. So, this term can be represented as omega squared, which is k by m, or omega is equal to square root of k by m. And what is this called? What's the term? Circular natural frequency. It's a circular natural frequency, right? So, so this is more accurately, this is called the circular natural frequency, and it represents radians per, it's represented as radians per. So, that is why it is just equivalent to going in a circle. That motion from back to forth, one full cycle is going in a circle. That is why you have, it's a particle omega so many radians per second, right? You think of it in that way. Now, here I will write this as 2 xi is equal to C by m, and I will add this term. We can start without adding and then add it, but we will just skip one step. Now, the term xi, I do not know if there is a better, am I saying it rightly? Psi, right? Something. So, this is a viscous damping factor. Now, if you see the units in this case, so C is in, what did we say, C is pound seconds. To understand some terms, I generally tend to look at what the units themselves are, and it helps you to again give a different perspective. The m is your mass, and mass is W by G, which is pounds per, in this case, let us say inches, inches per second square. So, pound second square per inch, these two cancel out, and omega is radians per second. So, this cancels out. So, you see all of them cancelled out, no units. So, that is why it is just a viscous damping factor. So, another, again, focus on what it means. Omega, which is the natural circular frequency, what is it dependent on? How many, what are all the factors? If I were to ask you this question, it is dependent on how many factors? So, stiffness, right? So, which means material depends on, what are all the different things stiffness is? Stiffness includes your load distribution, load type, let us say. It depends on geometry in terms of I and L, then boundary conditions. Anything else now? Here this is dependent on mass, right? See how we lump everything and we observe, and then you start breaking it down, and then you see how. So, if you are working in mitigation, right? Why do I show all this? You probably, it's there, but we don't become aware of it. You see the difference? You know that we calculate everything, but we are never aware of what are all, we go more fundamental. So now if you're working on mitigation effects, for example, you can look at a bunch of different things. How do I change materials? How do I change load types, geometries? How do they affect structure, right? So as Professor Ragappan was showing you there, he was doing foams. What's materials is different, internal structures are different. You can start varying all those things, right? So that's how you start. If you're in research areas, you look into each one of these boundary conditions. How do I change to get better? What do I want? I want a lower natural frequency, let's say. What all I can do? You have answers right out here. Why do you use foam, right? Why don't you use steel? All those things start coming into light. So more on, and this is from basic physics, more on omega. We know that the natural time period, this is the time, you can drop the word natural or include it. I tend to include because there is also a damped time period and damped circular frequency. That's why the term natural comes into, it helps. And if f is the frequency itself, the frequency is it's different from the natural frequency. This is 1 over Tn, right? So this is so many cycles per second, or simply it is expressed as 1 over second, or expressed as hertz. So the relationship between the two, as we all know, is omega is 2 pi f, or 2 pi divided by Tn. So if you see here, radians per second, this is radians, this is seconds, and omega is, so this is again, you can tend to get confused. Is it Tn by 2 pi or 2 pi by Tn? Happens quite often. Just remember this units, and that should bring you back to what the right one is. So xi, as we talked about, is a viscous damping factor. We have seen omega. So this is 1, let's say, but what about xi? This is basically a structural property which controls the stopping of vibration. There are a lot of external dampers, mechanical dampers. There are companies that make tunable dampers. Some of you may be familiar. It's a complete huge industry by itself, especially bridge applications, seismic applications. So, any questions? Somebody thoughts? Okay. So, given those two, wait, let me add a little bit more on dampers before I go to the next one. If xi equal to 1, psi equal to 1, this is what is results in your C is equal to 2m omega, we'll call this omega n, natural. So this is, we started with that definition. C is equal to for xi. So this is 2m omega n, and this is what is called a critically damped system. So this is 100% This is just to give an idea of the extreme case. This is a critically damped system. In other words, the structure dampens instantly. And none of your structures are anywhere close to it. We've seen the maximum it can go 10-15%, 0.15 or whatever it is. So, and of course, xi equal to 0, there is no damping at all. So, let us see the simplest case. The simplest case is where you have no damping and you have no external force. So, what you have, what it results is a free vibration problem. So, what we have as a simplified equation is, if I take out omega n square x equal to 0. Omega n itself is dependent on boundary conditions, we have seen that. So, here if I am going through the solution, we need, this is time dependent, so we need initial values. So, omega is boundary conditions. Solution to this expression x is, let us say, a cosine omega n t plus b sine omega n t. This is the solution. Now, this solution now depends on initial conditions. Initial is when time equal to 0. Again, my observation, again based on undergraduate, even in graduate level, people sometimes tend to see both of them as the same, initial and boundary. Initial is related to time and boundary conditions come in omega n. So, the initial conditions here are, let us assume, for example, at t equal to 0, we are looking in terms of x. It starts from x equal to 0 and t equal to 0, let us say x dot, which is your initial velocity, is 0. And when you apply them, here, the first condition that you apply, you are going to get a equal to 0 equal to a multiplied by 1 plus b times 0. So, this gives you a equal to 0, and the second condition you apply, you get 0 is equal to a was 0 anyway, plus b. Now, here if you do x dot, it is cosine omega n t, b omega cosine n t, which is x dot. So, at time equal to 0, this also goes to 0. Both of them, here you have now the cosine omega n t goes to 0. So, literally you have no solution, but two options exist, either b equal to 0 or cosine omega n t equal to 0. A sine b, I am sorry, yeah, a cosine b sine. So, this is fine. So, cosine m t. So, from here you can say cosine omega n t equal to 0, and it is 0 for cosine n pi over 2, right. So, from here you get n pi by 2 is equal to omega nt. And this is at t equal to 0. So, you get your omega n for different natural, this is for n equal to 1, so on and so forth. So, what you get as a function of x, this is an eigenvalue problem. So, you get this in terms of maybe something like this, or it could go the other way around. So, what you have here is a free vibration, this is your time period, and your initial conditions, of course, here I have expressed, it depends if your initial conditions, this is a very general solution I put, this would be your initial conditions, that would be the x dot 0, or it could be the other way around also, depending on the initial conditions that you apply. Now, this is just to start with to signify what Tn is and a free vibration problem is. But when you do to blast, we take the same thing, again no damping, and we'll spend some time on this. So, here now I include m x double dot plus omega n square x is now p of t. You have a forcing function. So, basically you have a system, you have a spring, mass, we will talk about mass equivalence later, but now you have a forced vibration. So, what we are going to get is functions of x, which are a function, both your x of t and the solution now you will have x of t and x dot of t. These are all functions of time, different functions of time that we will get out of this. Maybe I will just take a little digression to give you, before I do this, well, let us go back to the case of free vibration. I just want to show a graph that is very helpful to view. Free vibration with damping. We are not going to solve that equation here. So, you are considering the case of x double dot plus 2 xi x dot plus kx equal to 0, and with initial conditions x dot x equal to x naught and x naught dot at t equal to 0. What? Oh, this one, right? Sorry, omega square. Yeah. Now, the solution for this is given as e power minus psi omega nt multiplied by x naught cosine omega nt plus x naught dot, that's initial condition there, plus xi omega n x naught divided by omega d. So, this should be d, sorry, omega d, and I will show you what the differences are, sine of omega d t. So, with those initial conditions, what you get now is an expression that looks something like this. And it should be symmetric, doesn't quite look symmetric. So, and it should be even better than what I've drawn. So, if you plot it, you will see that the peaks are governed by this exponential function. So, this reduction is e power minus xi omega n t. So, damping results in reduction of the peak. The boundary conditions or initial conditions are reflected here. The initial slope again, this was your initial position and this is your initial velocity. And omega d, this is the damped circular frequency. And the damped circular frequency is given as omega n multiplied by the viscous damping factor. Again, while BLAST does not account for all this, these questions keep coming up frequently, especially when you start using programs. What do I put there? And hopefully this will help you understand what needs to be put. And for most cases, omega d is approximately equal to omega n for most situations, unless even if you take xi of 0.2, right, 0.2 is 0.04, square root of 0.96, it's almost, so that's 20% is a very high damping. So, that is also to be kept in mind. So, now let us come back to our case. So, a little digression, but when you develop the topic, I think we include, I prefer to include all these fundamentals. So, we are coming back to mx double dot plus omega n square x. So, let us now understand what happens when we apply a blast load to this expression x naught plus omega n square x equal to P of t divided by m, or we can have m here. So, now the mass comes into play and we call this forced vibration. Now, I am a little more thirsty today. So, this is a non-homogeneous differential equation. So when you have a non-homogeneous differential equation, what are the components? It has a x has 2, right? The homogeneous part of the complementary function plus particular, right? This is the homogeneous or the complementary part, and this is the particular solution. The particular solution is dependent on the forcing function, and both of them are functions of time. Okay. Now, what are the forcing functions? If I were to ask you, from what you have absorbed over the past 3 or 4 days, what would be a forcing function? And you have seen some experimental data also. What's that? Yeah, okay. So what is the nature of the forcing function? Oh, a little louder, please. Okay. So when I'm talking of forcing function, I'm looking for an answer in terms of P as a function, force as a function of time. So if I were to, what are the different types of forcing functions you and I have seen? I've seen it too. At least 3 kinds. Constant, yes. Where did you see the constant part? Or what is an application for a constant part? Oh, why is... So let's see why we consider these 3 scenarios. So you said the forcing function is constant, right? Who said, what did you say? Static load. Okay. So applications, but we are not, we will call this quasi-static here. Static loading is not part of this course. So quasi-static, but it is, quasi-static is not a real, we call it quasi-static because the blast load or whatever load looks like a static load. What's a industry application for this type of loading with reference to blast? And I heard that term one of the days, that application. You may not be aware of it. Vibrations. Anything, anybody else? I don't know who mentioned it. Nuclear industry, right? Who mentioned nuclear explosions once? I don't know, I was talking to one of you, and anybody working in that area here? I know I was not imagining that conversation. So, nuclear explosions tend to be, it's not exactly static, but this is a good example of constant load over a period of time. What have we been seeing frequently? Every day, literally. You've done a tutorial yesterday. Triangular loading, right? So how is a triangle looking? Okay, we've seen 2, but the simplest one is going down, right? Why did we took and we said this is P naught to 0 over TD. So you see how nicely it develops into some very simple, this is load duration. Practical applications, just take these basic differential equations and apply. We're just moving on adding a little more layers. Another, especially when you saw, so this is there's another type you saw in the lab that Professor Aragappan was talking about. So it can actually go, stay for some time and then, right. So here what you have to do for the forcing function, this was, what was the difference again, maybe the research scholars, you can talk a little bit about the difference. I think this may be a good time to reinforce that idea. I think Kavi, so you were talking about it. So which one is a blast and shock? So this is so the question comes often, right? Shock wave, and this is right? Can you maybe talk a little bit about when you see the differences? I know you mentioned that day, but everybody was dispersed and so that is in a shock tube type application, right? So here, and we will look at all three cases here. So this is a sharp rise and a drop. Here you have a linear rise, then sustained and drop. And the drop also you can either do, once you start putting exponential functions, so how will you represent P of t? So in this case, for the three representations, you get P of t equal to P naught. You get P of t is equal to P naught multiplied 1 minus, let us say this is t divided by Td. Now here you have Tr, that is why we have calculated rise times, right. In many cases, yesterday we were asking the rise time is 11 milliseconds, and in one case the rise time is 0.00 something, hardly anything. So you do have a rise time. So in this case you would say, anybody wants to take a shot? Let us say this is P naught. How would you represent this function? I don't want to spoon feed you. Complete the sentence. Okay. Okay. Good. Anybody else wants to add a voice to it? Another person take. Is P naught? Smart guy, took the easiest one from. Your turn is done. And some constant T by, you have seen this, right, Friedlander equation for T greater than. Now we will see how complexity adds, right. So when you represent this, when you are solving, I think we will stop with this. So the differential equation setup and we'll focus on all of them. We can linearize the last part, or we will. So when you do your differential equation setup, this is going to be fairly straightforward. You are solving the expression x, what was our, let me use the same terms, mx x double dot plus omega n square x is equal to p naught by m. Now, if I set this one up, this is p of t, I'm sorry, x double dot plus omega n square x. Now, you see this is a little more complex. It is, now we forgot to say this is from 0 less than or t less than or equal to td, and this becomes 0 for greater than td. So, you set this as p naught into 1 minus t by td for 0 less than x. I need to add something to it, right? So, that is my addition, my turn done. I can stop talking now. 0 less than t less than td, and then it is important to not forget that. We'll see why that plays a role. Why did I just add a 0 term? What importance you think it has? I could have just gone by what you said and moved on, and you would have accepted it. But why is it important to include that 0? Okay, that's definitely a point. So, this is 0 for t greater than td. So, what Amit saying is this is natural or vibration. One more aspect. Is this natural vib, or maybe let you answer first and then I will give you a clue if you're not able to. One more aspect to it. You'll stay here till you answer. Right. So, the boundary conditions, right? So, he's doing a PhD or he's almost finished. So, so you see how you absorb more as you study further on. At t equal to td, so this is one. The second aspect is at t equal to td, x of td and x dot of td, these become initial conditions for the free vibration problem, right? How do you, so if somebody asked me, that's why I drew this, I was hoping to ask a question, what is x naught, what situations you might see, because normally building starts with, anything starts with 0 conditions, right? So, I was hoping there a question would come. But now, here if you look at it, you have to set up not just this is exponential, or you can linearize it and then set this up to 0. How do you linearize it? What would you do to linearize that function? Because solving the exponential part in the differential equation is going to be harder, much harder than a linear drop. what would you do to linearize that function? Expansion. Any other thoughts? Little up. Logarithmic expansion is what you're talking? Okay, that's one idea. We've talked of this idea before. We've done this idea a lot. We implemented this practical concept, easy concept before. Equivalent triangular, so impulse equivalence, right? Yeah. So you can use, very good, impulse equivalence. I'm not going to ask you to do any of these solutions, so don't start sweating. Or maybe I should. Equivalent during tutorials. Use impulse equivalence to, I don't know if this is a word, triangularize. Triangulate, no, not triangulate. Triangularize is probably better. And then, so this leads to, let's say this is TE, then equal to 0 for T greater than TE, right? So now you would set this up as, again, all of this is without damping. You would P naught T by TD, P naught 1 minus T by TE minus TD, I think, equal to 0. So this is for T less than T1, T1 less than T less than, we haven't put those, but you know what we are talking about. TR to TD, then TD to TE, and greater than TE, right? So you have to set up 4 different differential equations and then solve it. Well, you're lucky. You don't have to solve. So that's where we will use, we will consider, we'll consider these two for looking at it. This is, we will see this is the easiest. Make sure, let me save this. So what we will do is, we will solve this by hand in the next session and look at, study the characteristics. What's coming up is understanding the science and also the physical behavior of the solution. For all of these and more, now, how does a shock tube, what we didn't talk about was, you've seen, I'm glad, how does the pressure versus time look like? It looked, whatever it is, right? It's got all kinds of, and you saw other whatever variations, right? So it can be very arbitrary. For these also, we will use a program called nonlinear. For solutions. And for this also, we will look at charts. In those before nonlinear existed, or there are others, not this is, you can develop your own also using numerical integration procedures for differential equations. And then we will study how to use charts for scenarios like this, or even a scenario like this one, all three cases, and then solve some problems in the second session.